Okay, so I'm going to show you how to do a net ionic and a complete ionic equation. The complete ionic equation is everything. The net ionic, you take out the spectator ions. I'm going to show you what that means in a minute. Now, these are your notes, solutions in net ionic. I put all of the answers up on Google Classroom. And I put a lot of like my little notes and stuff, obviously, especially on this page. One of the things you're going to have to really remember is you need to make sure that you know what a strong acid is. Usually what I do is I just memorize them. Binary acids are always strong, which means like HCl, HBr, HI. When I say binary, I mean an H and something else, and that's it. Okay. If you have ternary acids, if your number of oxygens exceeds the number of hydrogens by 2 or more, it's strong. So let's go over here for a second, like this, for example. Your number of oxygens is 4. Your number of hydrogens is 2. It's double. So it exceeds, the number of oxygens exceeds the number of hydrogens by 2. Sulfuric acid is strong. Here's my hint. Sulfuric acid is strong. Phosphoric acid is strong. Then like mostly it's just like your HCl, your HBI, your, you know, like your hydrochloric, your hydrobromic, those kinds of things. Most of the time you're going to see sulfuric and phosphoric. Those are going to be the two big ones. And the thing you need to know about that is strong acids are always aqueous. Weak acids, if you happen to run into one, which you probably won't for our purposes, are written in their molecular form, which means they're usually a liquid. But don't worry about that. Just worry about making sure you know what your strong acids are. So sulfuric, phosphoric are the two big ones. Hydrochloric, hydrobromic, hydroiodic, those are the ones you're going to run into. Really, seriously, to be really honest with you, sulfuric, phosphoric, and hydrochloric are the only ones you're going to run into. So anyway, those are always aqueous. I just wanted to throw that out there. So one of the things I did in the notes is I did these practice problems, but I recopied them because they were super messy over here. I made a mess. So I recopied them. I did 1, 3, 5, 8, and 10. If you can do number 10, you can do anything. One thing you have to be really careful about is you need to you need to know, like right here, for example, that Cr means crystal. Crystal's a solid. So crystal, solid, same thing. So not same thing, but you know, crystal is a solid, so that means that a reaction happened. Because they love to throw that kind of stuff in there for you, of course, because you know how they are. The other thing I ran into that you're going to want to notice is down here in number 10. Over here, this is Cr plus 2. Over here, it's Cr plus 3. Still the same ion, even though it's, you know, one more different, you know, it's a different charge. You can go ahead and cross those out. I'll explain what that means in a couple minutes. Now, backtracking. Sorry. Okay, we have our double replacement reaction. Net ionic, complete ionic are always double replacement reactions. They have to have something in the products, a solid, liquid, or a gas in the products. Most of the time you're going to have a solid. Sometimes like this one, you'll have a liquid. We already said that H2SO4 was aqueous because it's a strong acid. But if you want to use your chart, you can find sulfate. Yeah, sulfate, sorry. You can find sulfate. Sulfate is soluble unless it's with CaBa, Pb, Sr, Hg2, or Ag. It's not with any of those, so it's aqueous. It's with hydrogen. KOH, we have to look up. We look up the OH. Hydroxides are insoluble unless they're with Ba, an alkali or an alkaline metal, except Be. K is an alkali metal. Hold on. Just want to show you. K is right here, so it's an alkali metal. Okay, first row, alkali metal. So because it's an alkali metal, this is always aqueous. This is also aqueous. Okay. Over here, water, always a liquid. Okay. I know that it can be a solid or a gas, but we are talking about room temperature here, so it's liquid. K2SO4. We're gonna look at sulfate again. Sulfate, SO4, is soluble unless it's with Ca, Ba, Pb, Sr, Hg, or Ag. It's with K, which means that it is aqueous. okay? Because it's soluble unless it's with those. The only time it's a solid is if it's with one of these. So it's aqueous. So we know we have a reaction here because we have aqueous, aqueous, we have liquid and aqueous. So in our products, we have a liquid, so we know we're okay. Now, watch what we're gonna do. When you have a net ionic equation or complete ionic equation, because you do that first. Complete comes first, then net. Right now, seriously, I don't care if you know what a complete ionic equation is, because it's not really that important. It's kind of a step in the way to making a net ionic equation. So, but just bear with me. So when you're doing a net ionic and a complete, when you're on your way to a net ionic equation, doing a complete ionic equation, the first thing you have to do is everything that has an AQ gets broken down into its component ions, okay? So you disassociate it. The reason you do that is because if it's aqueous, when you put it into solution with something else, what's gonna happen is all your ions are gonna break apart. That's why they rearrange over here and end up with other partners, because they disassociate. Okay, so here you have two H pluses. So 2H plus. Always, always, always put your AQ after your ion. Plus, you have one SO4, and SO4 is -2. I know that because I memorized my polyatomic ions. AQ, okay? This is AQ, so it's going to break down into its component ions. You have a K plus right here. It's AQ. This is an OH minus, and I'm going to run into this. This is one of the issues you have with this, is that you always run out of room. If you happen to look at this over here, look at this. To show you where my other one was. Look at all the, like, I ran out of room all over the place. I had to go up in the air and all over there. So it's a really big problem with these. So what yields, and I'm just going to come down here with this stuff over here. So this is a liquid. If it's a liquid, a solid, or a gas, it stays like it is. It does not disassociate, okay? That's how you know you have a reaction. So you leave H2O alone, okay? Bring its coefficient down, bring it down, stay like it is. It just comes straight down. Plus, this one's aqueous, so you have to break it apart. You have two Ks, K is +1. You know that from the periodic table. Put your AQ after it. SO4 is -2. You know that because I memorized my polyatomic ions, okay? So now, this right here, this lovely thing right here, is your complete ionic equation, okay? So when I say complete ionic, what I mean is you take your molecular formula, or balanced molecular formula. These are in their molecular form, okay? So you take your balanced molecular formula, you break it apart into your complete ionic, and then you take your complete ionic and you cross things out to get your net ionic. So watch. What we're going to do is we're going to take out anything that's a spectator ion. A spectator ion is an ion that shows up on both sides of the equation, but isn't really doing anything, okay? Like, see how SO4 -2 is right here, and SO4 -2 is right here, and K1 is right here, and K +1 is right here. They didn't balance this correctly. That's nice. Sorry. Anyway, so this should be 2. This should be 2. Sorry about that. I just pulled this out of the notes and they didn't balance it correctly. They balanced it. They put a 2 there, but they didn't balance anything else. But anyway, sorry. Anyway, so have 2 there. So let me backtrack just a second. So the reason I have 2 Ks here, and I just went back and balanced it just now, but the reason I have 2 Ks here is because there's a 2 in front of the K. So if I just gave you 2 KOH, you would say there's 2 Ks and there's 2 Os and there's 2 Hs, right? Now, OH is a polyatomic ion, so you have to just do 2 OHs. So, but you have to bring that with the K too. And there's a reason why I kind of paused there, and I was like, wait a minute, why do I have 2 Ks over there and not on there? So here's the thing. You have to have the same number of ions on both sides. If your equation is balanced correctly, which of course it wasn't. Sorry, thank you, notes. Anyway, if your equation is balanced correctly, then you'll have the same number on both sides. unless they put in a trick for you, and then sometimes you won't, but just be careful with that. Number 10 is a good example of that. So anyway, back to what I was saying. So you have an SO4 on this side and an SO4 on that side. We're just going to cross them out because they cancel. You have 2 Ks here and 2 Ks here. They cancel. You have 2 H's here and 2 OH minuses here, but on the other side you don't have ions. Sorry. You have the molecular formula of H2O. So you have ion, ion, molecular formula, okay? So that means you can't cross out H2 and OH because they're not spectators. They're actually doing something. Spectators just sit and watch, right? These guys are actually doing the reaction. The 2 H's and the 2 OH's are coming together to form 2 H2O. That is your net ionic equation. So all you do is bring down anything you didn't cross out. So 2H plus plus 2OH minus yields 2H2O. That right there is your net ionic equation. Okay? Again, when you're dealing with spectator ions, you're looking for ions on either side. Be really careful. Those of you who still don't know your polyatomic ions, you're going to have to look these up. If you don't know how I got K and OH together with 1 K and 1 OH, you're going to have to go back and figure that out, because you're not going to be able to do the net ionic if you don't know how to do those basics, which is what I've been telling you all year. I've been telling you, you need this later. It builds on itself. You have to know how to do this. But if you're still struggling with stuff like that, and like this right here with K2SO4, you don't know why there's 2 Ks there. There are 2 Ks there because K is +1 and SO4 is -2. If you don't know that, if I were you, I would go to Bozeman Science on YouTube and look up how to create ionic formulas. Okay, but most of you are okay. This is just, don't let this scare you. It's a lot of messing around. Don't let it scare you, because you can do this. Okay, I'm gonna put this video up. You have the notes, you have my answers. Please, 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 if I made any silly mistakes, let me know. Here comes Dozer. If you have any questions, again, send me a reminder. Okay, bye.